A general formula to calculate the area of any regular polygon. Shapes are to be seen everywhere. In the streets and in our houses, we see many shapes. For example, look at the shape of a stop sign in the street, or the yield sign, or the web of a spider. And what about the tiling on a floor? We do see lots and lots of shapes, familiar shapes in manufacturing. Here we have a clock that is manufactured, and there is a certain shape that we associate immediately with it. Some other items from manufacturing, even calendars, some three-dimensional shapes as well. What about the soccer ball? And on the surface area of a soccer ball we have certain familiar shapes. In nature we have a whole range of familiar shapes. So many amongst flowers and leaves. What about the shape, the pentagon, five-sided regular shape of a honeycomb? If you have the cross-section of an orange, you see there's very interesting regular shapes, apart from the fact that an orange is normally round. And amongst the animal kingdom, there, for example, we have so many familiar shapes. So it is clear that shapes play a vital part, fundamental part in our everyday experience, and these shapes are categorized. And also so in mathematics, we have many familiar shapes, and they play a very important role in geometry and other sections of this particular subject. In what follows, we will introduce and discuss key concepts that are used to describe or categorize two-dimensional or three-dimensional shapes in a mathematical way. Now, some of these concepts will include length, area, volume, and related concepts. Let us first of all look at the concept of length and the units of length for the sake of measurement in this case. Here we have the scale in terms of what we can utilize to measure length, in this case within the metric system. And from right to left we have the millimeter as a unit, centimeter, decimeter, meter, decameter, hectometer, and kilometer. Now some of these units are well known, others not so well known, but let's just see how they relate to each other on a scale as we move from the smallest millimeter to the largest as indicated on the screen, that is the kilometer. Now in this case the names for the units, of course, as listed, can be distinguished by the order in terms of the size of, relative size of the unit for length. In our case, if we move, for example, from 1 kilometer to 1 hectometer, you have to multiply by 10. Why is that? Because a kilometer as a unit is order 10 times greater than the hectometer, and so on. The hectometer 10 times greater than a decameter 10 times greater than a meter, and so on with respect to the decimeter, the centimeter, and the millimeter. So each is 10 times greater than the next if you move from the kilometer down to the millimeter. So the order difference between the kilometer and a millimeter as a unit of length is 10 to the power 6. You see, you have to multiply with 10 6 times to move from 1 kilometer to the equivalent number of millimeters. And clearly, if we want to convert, in this case, a millimeter, or move from millimeter to centimeter, becomes a bigger unit, again decimeter and so on, you have to divide the number of units that you start out with, in this case, by 10 for each step in this particular chain. Now let us have a look at a case where we represent millimeters, in this case 5,365,470 millimeters. So the units digit always carries the decimal to the right of the 0 in this case, and it is linked to the unit millimeters. If I would like to represent this exact measurement centimeters, clearly the decimal position will shift 1 to the left, and then I can say I have here 536,547 centimeters. And again, if I shift the decimal one position to the left, I will be measuring the same particular length unit in decimeters, and then I will have 53,654.7 decimeters, and so on. So to convert from one unit measure to another, here we have some more examples. Say we have this particular measurement, 53.6547, in this case hectometer, and I would like to express it as meters, the same measurement. Then clearly the decimal position must shift 2 units to the right. That means I've multiplied by 100, or 10 to the power 2. As we can see, hectometer to meter, there is 2 orders of 10 to the power 2 that I must multiply with, and in this case it means the decimal point, or the decimal comma for that matter, will shift 2 units to the right. And from meters to millimeters, we have 3 units or 3 positions for the decimal to move to the right, since I multiply by 1,000. And if I convert millimeters again to kilometers, in this case I have to shift the decimal, which is to the right of the 0 here, 6 positions to the left, in order to get 5.36547 kilometer. So these are some examples of conversions into equivalent measurement using a different unit of length, and make sure that you try a number of examples that are similar to this. Note, in this case the name of the length unit is linked to the units digit, as we have seen here that we started out with. So to the right of this final digit, on the right hand side of the expression, is in fact our units digit, and to the right of that will be the decimal point, and that is linked to millimeters in this case. And we can actually populate the units of length measure to go along with the positions, digital positions, to the power 10 to the left as indicated. Now this method is fairly important in terms of changing from one expression to another in terms of the units of length. And also remember, length, in this case, units of length will be a one-dimensional representation, or a quantity in this case. Next we consider area units of measurement, which is of course two-dimensional. So the units of area measurement in the metric system we can represent similar to what we did for the length measurement as a one-dimensional unit of length. In this case we have the area as a two-dimensional measurement of area. So we start with the millimeter square. Can you see the only difference is that everything is now squared in terms of the unit measure that we've had before for the length measure. So in this case, to move, for example, from millimeter squared to centimeter squared, previously we had a order 10, now it will be an order 10 squared. So everything squares in terms of conversion from one area unit of measure to the other, if you look at the metric system. And here we have a nice representation to tell you exactly how to move from one area measurement to another one, as indicated on the screen. For example, square kilometer, kilometer square or square kilometer, if you want to change that to, in this case, square hectometer, then there is a factor of 100 that you have to multiply with to move from square kilometers to square hectometers. And that is just 10 squared. Previously we had a factor of 10 for the unit from kilometer to hectometer. Here we have 100, 10 squared, from square kilometers to square hectometers, and so on. If you move from left to right, you have to multiply with each conversion in this particular representation by 100, and of course if we move the other way, changing square millimeters to square centimeters, for example, you have to divide by 100, which is 10 to the power 2. Previously we had to divide by 100 if we look at the length measurement, which is one-dimensional, but here we deal with a two-dimensional unit of measurement. So let's have a look at an example where we convert from square meters to square kilometers, and after that to square millimeters. Question is, how do we represent this particular given measurement, 386.742 square meters, in relation to the other units of area measurement in the metric system? Here we show how to do that. clearly we have our decimal point with a 6, which is the unit digit in this case, and it's given in meter square. That is always our reference. Since we have a two-dimensional unit of measurement in this case, we're linking the pairs of digits as indicated to the left and also to the right, together with the units of area measurement in the metric system as indicated. That gives us a way of just making sure that we keep track of if we move from one unit to the other in terms of the area measurement. Note also that each the measurement or unit is represented by a two-digit number here, and the name of the unit is linked to the units digit. In this case it is given as square meters, and we link that to the units digit 6, in this case 386, and that then is the starting point in order to populate to the left and to the right in pairs of digits as indicated. Now we have to convert then, for example, the 386.742 square meters to square kilometers. So can you see, we can just have a look at this representation, and in our case we know that from meters to kilometers we have to divide by 1000 squared, or 10 to the power 6. Normally it's 1000 from meters to kilometers that you have to divide by, but now to square that means it's 10 to the power 6, or 6 positions in the decimal system. So it's 2, 4, 6, and there we have the representation then, in this case 3 zeros, and then 386, 386, and then of course 742 as well. All the digits to the right follow, because this decimal position have shifted 6 units to the left to get 0.000386742 square kilometers. In order to convert square kilometers to square millimeters, on the other hand, we need to see what we start out with, square kilometers. So the unit digit will be linked to the kilometer squared, so we have a position right here, and then the decimal position must shift 12 units to the right, since we have to multiply by 10 to the power 6 all squared to get from square kilometers to square millimeters. And if we do that, 2, 4, 6, 8, 10, and then 12, we see exactly what we have here. The in this case the number of square millimeters will be 386,742,000 square millimeters if we convert from square kilometers to square millimeters. Normally from kilometers to millimeters, the one-dimensional case of length measurement, there will be 1 million, so 10 to the power 6 factor, but now we square that, so we have a 10 to the power 12 factor, which means that the decimal point will shift 12 positions to the right compared to what it was when we have started in this position. We will finally consider a three-dimensional unit of measurement called volume, and the space in 3 dimensions that will be occupied by such a unit will be referred to as the capacity. So here we have the units of volume measurement in the metric system, ranging from millimeter cubed to kilometer cubed. You see, the exponent in this case indicates it's a three-dimensional unit measurement in such a case. Now the capacity that corresponds, for example, to a cubic centimeter or centimeter cubed will be the milliliter in this case. So if we have, for example, 1 cubic centimeter is occupied by a liquid, for example, whether it's water or something else, then we say we have 1 milliliter of this liquid. Similarly, the cubic decimeter in this case will correspond to the capacity of the liter. So 1 cubic decimeter will be 1 liter. And similarly, a cubic meter will be a kiloliter, if you refer to the capacity correspondingly that goes along with this particular three-dimensional unit of measurement. Now, note that the volume unit system of measurement is a base 1000. It's three-dimensional, so it's 10 to the power 3 to move from one unit to the next in this particular range of metric unit measurement that we have on the screen. Whereas the capacity unit system is a base 10 unit. In other words, if we, for example, want to convert 1 cubic meter or correspondingly 1 kiloliter to liter, it is a order 10. In other words, we have 10 liters makes 1 kiloliter in this case. 1 milliliter to 1 liter, then you have to divide by 1,000, or alternatively, if we want to convert 1 kiloliter to a liter, you have to multiply by 1,000. Although we have, in the general sense, the capacity measurement, in this case, the units listed below as milliliter, centiliter, deciliter, liter, like we normally would, indicate the one-dimensional unit of, for example, length measurement for that matter. So we have a decaliter, hectoliter, and a kiloliter as such. Note then the correspondence between the volume measure and the corresponding capacity measure as indicated. Cubic meter corresponds with kiloliter, cubic decimeter with a liter, and cubic centimeter with a milliliter as indicated. For example, let us convert the following volume measurement, 386.742 cubic meters, to kiloliter, liter, and milliliter respectively. We first convert the volume measurement to a representation where we link it to the units of volume measurement in the metric system as indicated, very similar to what we have done for the area and for the length measurements respectively. In this case, however, we know that each of these units will be represented by 3 decimal positions as indicated, starting with the units digit for the given volume measurement. The 6 corresponds to the cubic meters that was given to us. We have that the 3 digits as indicated, 386, will be linked to the cubic meters, and to the left and to the right, the decimal positions in triples as indicated will be linked to the units as indicated, since we have here volume being a 3-dimensional unit of measurement. Now, to move from cubic meters to kiloliter, liter, and milliliter respectively, or to transform this particular measurement as requested, we have to, of course, look at the number of positions to the right and to the left that will represent kiloliter, liter, and milliliter respectively. But note that cubic meters correspond to kiloliter. So we have, in fact, here also 386.742 kiloliter. To change this into liters, we have to multiply by 1,000, or 3 decimal positions for this particular point to move to the right, and hence we have this corresponds to 386,742 liters. Note also that this corresponds to cubic decimeters, as we have discussed before. To change liters to milliliters again, another 3 decimal positions, so we have to multiply with 1,000 if it moves to the right, as it should. We can see, for example, from the liter to the milliliter, or cubic decimeter to cubic centimeter for that matter, we have to move 3 units to the right, and hence we have, in this case, that the given volume measurement corresponds to 386,742,000 milliliters in this particular case. Next, we will consider areas of polygons, in particular a strategy to determine the area of regular polygons. Let's consider the following representation of a number of regular polygons. Now, a polygon, of course, is a 2-dimensional figure with sides, a number of them, and vertices. Here we have 5 vertices and 5 sides for a pentagon, and if the pentagon is regular, it means the side lengths are all the same in this case for this shape. So a regular polygon is then a shape where the side lengths are all the same. For the regular hexagon, we have 6 equal side lengths in this case, and we have also 6 vertices as indicated. Similarly, for a regular heptagon with 7 side lengths and a regular octagon with 8 equal side lengths as indicated. Now, for all of these regular polygons, we can consider a center point which is equidistant or the same distance from each one of the respective vertices. And we can construct lines as indicated. Now, a question would be how to determine then the areas of these shapes below, that is, of the regular polygons as indicated. A strategy in this regard may be, if we know the area of any one of the blue triangles in any one of these polygons, then we can determine the area of the respective regular polygon by just multiplying by the number of side lengths. For example, for the regular pentagon, if we can find the area of the blue triangle as indicated on the screen, we can multiply that with 5, since all the other 4 triangles that make up the area for this particular regular polygon will be identical, and in such a way we can find the area of the regular pentagon. So knowing the area of the triangles as indicated in blue, we can just multiply by the number of such triangles that make up the area of the respective regular polygon, and in such a way we can find the area of a regular polygon. This is what we will do in the next slide. Consider the strategy that we have discussed in the previous slide to find the area of polygons. In particular, let us consider the area of a regular octagon. First of all, you should know that the sum of the exterior angles of any polygon with n sides, let's refer to that as an n-gon, is 360 degrees. The measure of each of these exterior angles will be 360 degrees divided by n. Also, the measure of each interior angle of such a polygon with n sides will be 180 degrees minus this particular angle, 360 degrees divided by n. What happens if we apply this to an octagon where we have 8 equal side lengths as indicated? Here we have a representation of an octagon, and the exterior angle for an octagon is demonstrated. That is the angle between the side and the extension of an adjacent side as indicated. So this corresponds with a formula, in this case, where n is equal to 8. 360 degrees divided by 8, of course, is 45 degrees. So this then gives us the measure of each of the exterior angles of an octagon. Also, the interior angle for an octagon will be the angle that resides with each and every vertex as indicated. And in this case, if we apply the formula where n is equal to 8, then we have 180 degrees minus 45 degrees, which is 360 degrees divided by 8 in such a case. Now we get to the question, what will be the area of a regular octagon with side length 6 centimeters? So here we have the octagon then. We know each side has length 6 centimeters, and as discussed before, we can divide the area of this particular octagon into 8 equal, in this case, isosceles triangles, the same as the blue one as illustrated. Let's take one of these little triangles and make a construction as is indicated. Note also that the angles obtended at the center point for each of these triangles will be 45 degrees. That's what 360 degrees divided by 8, of course. There are 8 such triangles. And as we saw, the interior angle measure is 135 degrees. This explains, of course, the angle within each one of these particular triangles linked to the side length will be 67.5 degrees each. A isosceles triangle, that is 135 degrees divided by 2 for each of these two angles as indicated. And we construct a perpendicular line from the center point to the side length as indicated, and let's call this distance from the center point to the side length as indicated, the center point of the side length, as h. So we know this distance from the vertex to the center of the side length will be 3 centimeters. We have a right triangle that we deal with, and we have the angle 67.5 degrees. With that then, we're ready to try and find the area of each one of these 8 identical triangles that makes up the area of a regular octagon. In our case, the tan of 67.5 degrees will be h divided by 3. That is clear from the right triangle that we constructed. Therefore, h, the height from, or the distance between the center of a side length and the center point for the octagon, will be 3 times tan of 67.5 degrees. In this case, this will be a measure in centimeters, as the side length is given in 6 centimeters. Hence, we can now calculate the area of the blue triangle in the representation, or any other one of those 8 identical triangles for that matter, as half times the base times the height as indicated. So we have a half times the base or side length, 6, times the height, which we have indicated as h, is equal to 3 times tan of 67.5 degrees. Note that this measure will be in square centimeters, since it represents the area of such a little triangle. And finally then, the area of the regular octagon will be 8 times this particular area of any one of those small triangles. Multiplying out using your calculator, we get to a measure, in this case, area measure of 173.82 square centimeters. That is accurate to 2 decimal places. We can make use of the information that we have considered in the previous slide to find a formula for the area of any regular polygon. Doesn't matter how many sides it has. Let us consider such a general polygon within side lengths. We know that the measure of each interior angle is given by this particular formula, 180 degrees minus 360 degrees divided by n, where n is the number of sides of such a regular polygon. Let's say this angle in general is theta. Now, here we have a construction, say, of such a regular n-gon or polygon with n sides, just a part of it. We know that theta, as indicated, will be the interior angle for such a regular n-gon or polygon with n sides, and we can, exactly as we did in the previous slide for the octagon, make a construction linked to each one of the little triangles, the n identical triangles, which makes up the area of such a regular polygon. And the distance again from the center point to the side, or the midpoint of the side length, as indicated, will be indicated as h. Let's say this is the height of the triangle. We have an isosceles triangle as before, and clearly the angle in this case linked to the side length for the isosceles triangle will be theta divided by 2. Just half the angle, that is the interior angle for such a regular polygon. And let's indicate the side length as distance s for the purpose of generating the formula for the area of such a regular polygon with n sides. Now, clearly as before, we have that tan of theta over 2 will be opposite over adjacent. If you look at this little right triangle, where we have the angle theta over 2, that's h over, in this case, s over 2. That will be opposite over adjacent. That is the tan of theta over 2. And this, if you rearrange, just check this, make h the subject of the formula. We have a little formula here, s times, that is the side length, s times tan of theta over 2, everything divided by 2. Now, if we have this, we can now find the area of each one of these little triangles. The n triangles will make up the area, or the area for all of those end triangles will make up the area for the regular polygon. The area for each one of those triangles then will be given as a half times the side length, in this case S, times the height expressed in terms of the angle, that is the interior angle, and the side length S. As we have it here, so we take this formula for H, we put it in position here, half times the base times the height. Base in this case is the side length S. The height is given by this formula which we have deduced, and just combining this we can express the area of each one of these little triangles, identical triangles within such a regular polygon with n side lengths, as S squared times tan of theta over 2, everything divided by 4, where of course S is the side length for such a polygon. Hence we know that the area of a regular n-gon or polygon with n sides, equal sides, can be given as n times S squared, that's the side length squared, times tan of theta over 2 divided by 4, where theta of course is the interior angle for such a regular polygon. And of course the measure in this case will be area in square units. If the measurement of the side length is given as centimeters, this will be square centimeters, and so on. We will conclude this section by looking at an application of the general area formula for regular polygons that we have considered in the previous slide. In this slide we will particularly look at the regular quadrilaterals and triangles. So, the area formula once more for a regular n-gon that we have developed is given on the screen. So we have the order of the polygon, the number of side lengths, that is n times the side length S squared times tan of theta over 2, where theta is the interior angle for the given regular polygon of order n, with n sides, that is. Everything divided by 4. This is the area formula for any regular n-gon or polygon of order n. Let's see how we apply this in the case where we consider a square with side length S is equal to 12 centimeters. Now we all know that the area of a square will be in this case just 12 squared, which is 144 square centimeters. Let's have a look and see if this formula gives us the same answer in this case. Clearly we have n is equal to 4, because you should realize that a square is just a regular polygon of order 4, or a regular polygon where we have 4 side lengths in this instance, and also the interior angle is clearly 90 degrees for a square. So we have tan of 90 divided by 2, or tan of 45 degrees, that have to be considered as part of this formula, and that gives us plus 1. Tan of 45 degrees is 1. So applying the formula then to find the area of the square or the regular polygon of order 4 will be 4 times 4 side lengths times the side length 12 squared times 1 divided by 4. Of course we get the answer as we should, 144 centimeters square, or square centimeters. Let's also apply to the case where we have an equilateral triangle. Note that the equilateral triangle is also a polygon of order 3. 3 side lengths equal lengths makes an equilateral triangle. And let's say the side length in this case S is equal to 6 centimeters. Applying our formula, we know that n is equal to 3, and tan of theta over 2, what will be the interior angle of an equilateral triangle? Clearly 60 degrees. All 3 of the angles will be 60 degrees, the interior angles. So we're looking at tan of 30 degrees as part of the formula to find the area of such a triangle. And tan of 30 degrees, you should know, is 1 divided by the square root of 3. So apply this now to the formula. We know that the area of a polygon of order 3, where we have 3 equal side lengths, or just an equilateral triangle for that matter, will be 3 times 3 side lengths, that is, times a side length is 6 squared times 1 divided by the square root of 3, everything divided by 4 from our formula. And if you put this together, we can express this as 9 times the square root of 3 square centimeters. Now please check this. Just construct a little equilateral triangle with side length 6 centimeters and just find the area in a traditional way as you used to, and make sure that your answer agree with this. So here we have applied then our general formula for finding the area of a regular polygon of order n. I think you're ready now to tackle a tutorial on the areas of regular polygons. In tutorial 1, we're given a regular pentagon in which each side measures 10 centimeters as indicated on the screen. You have to determine, in this case, the interior angle measure. Secondly, the height of one of the 5 isosceles triangles as indicated. The area of one of the 5 isosceles triangles, since they're all identical. The area of the regular pentagon as a whole. And finally, you have to use the general area formula to confirm your answer that you have calculated in part 4 of this tutorial. At this point in time, I suggest that you pause the video, do tutorial 1, and then come back and view the solutions. Let us consider the solution for the first 2 parts of tutorial 1. Here we had to find the interior angle measure of a regular pentagon in which the side measure is 10 centimeters. We also had to find the height of one of the 5 identical isosceles triangles that makes up the area of such a regular pentagon. Here we have the representation of the pentagon with side length 10 centimeters, and in this case the measure of each interior angle, according to the formula that we considered before, will be 180 degrees minus 360 degrees divided by 5, since n, the order of the regular polygon in this case, is 5. Pentagon means 5 equal side lengths. If we substitute n equal to 5, we have that the measure of the interior angle in such a case is 108 degrees, as indicated. This is the angle, of course, that is associated with each vertex of the regular pentagon in this case. Also, the height of one of the 5 identical isosceles triangles, we have constructed one of them, that is defined by the center point for this regular pentagon, and the vertices, 2 adjacent vertices as indicated. And if we now drop a perpendicular line from the center point onto the side length and have the midpoint of that side length as indicated, we know that this defines the height of the triangle that we're looking at, but also defines a right triangle as indicated in green on the screen. Now this particular right triangle is important. The height, the one side length, is 8 say, and we know that the second side length, in this case linked to the right angle, is 5, that's half the side length 10, and this angle is also half the interior angle for the regular pentagon, which is 54 degrees. So with that in hand, we can find an expression for the height of one of the 5 isosceles triangles as was requested. We know that tan of 54 degrees will be opposite divided by adjacent, that's h over 5, and if we rearrange, we know that the height can be expressed in terms of the interior angle, in this case as 5 times tan of half the interior angle, which is 54 degrees. And if you calculate this, it's more or less equal to 6.8819 centimeters. That is to 4 decimal place accuracy in this case. In parts 3, 4 and 5 of tutorial 1, we have to find respectively the area of one of the 5 isosceles triangles, the area of the regular pentagon as a whole, and then we have to use the general area formula that was developed earlier in this lesson to confirm the answer in part 4 of the tutorial. Here we have the pentagon again, and what we have from part 2 is that h can be written in terms of the interior angle, or half of the interior angle, as 5 times tan of 54 degrees as indicated. Now, the area of the isosceles triangle in question would be half times the base times the height. So here we have it. Half times the side length is the base, in this case 10 centimeters. There we have it. Times the height, which we have an expression for, 5 times tan of 54 degrees, which gives us then more or less 34.4095 square centimeters. This represents the area of this particular isosceles triangle, and 5 of them actually covers the area for the pentagon, a regular pentagon in this case. So the area of the regular pentagon, that is part 4 of the tutorial, will this be 5 times this particular number, 25 times tan of 54 degrees, which gives us, of course, the answer of 172.0477 square centimeters. Just check that you agree with this, having done this by using your calculator on your own. And also, if you look at the area formula that we have developed earlier in this lesson for a regular n-gon or a polygon, where we have n side lengths, equal side lengths, we have seen the formula a quarter times n times the length of each side, s all squared, times tan of half the interior angle for such a regular polygon of order n. If we apply this formula now in this case, where n is equal to 5, and the angle that we're looking at, the interior angle, theta is equal to 108 degrees, and substituting into this formula and calculate, just check this, we have exactly the same answer. So this then, of course, agrees with what we have calculated in part 4 of this particular tutorial. In lesson 2 of this video, we will focus our attention on the area of shapes. Let us consider the outcomes for lesson 2. In this lesson, we will focus on area formulae of the square, a rectangle, triangle, trapezium, parallelogram, and the circle. We will be calculating the areas of these shapes, and finally we will be investigating the effect on area if one or both dimensions of a two-dimensional shape is multiplied by a constant factor. Let us now look at the area formula for familiar shapes. We start with the basic square. That's a quadrilateral where the side lengths are all equal and you have an angle of 90 degrees associated with each vertex. In this case, if the side length is s, we have the area is s squared. That should be familiar to all of us. Rectangular, similarly, we have a 90-degree angle at each of the vertices. In this case, it is a polygon of order 4. It's not regular, but we have two pairs of sides have equal length. So we have a length side B and the length side H, and the area in this case is just the product of the two sides. That's the length and the height, for example, if you would like to put it that way. Now, a triangle in general, the area would be given by a half times one side length, which is considered as the base B, and the height, the perpendicular height from the third vertex. If you drop a line perpendicularly to the baseline, in this case, as indicated, and the distance from the vertex to the opposite side, h, will then determine the rest of the formula for the area. So a half times the base times the vertical height of this particular triangle then gives us the area. Trapezium, obviously defined by two side lengths being parallel in this case. We have that the area of such a shape is given by the average length of the two parallel sides, that's a plus b divided by 2, multiplied with the distance between the two parallel lines. That gives us the vertical distance between the two parallel lines as indicated. So the area of a trapezium then will be the distance between the parallel lines multiplied by the average of the lengths. In other words,
in lesson 2 of this video, we will focus
a parallelogram is just
on
a
the
special
area
case of a trapezium in that
shapes.
sense, where we have that the other two sides are also parallel, two pairs of parallel sides. So again, in this case, the lengths of the parallel sides will be exactly the same. So the average will just be the length of a side, the average of the two side lengths, times, of course, again, the vertical distance between the particular pair of parallel sides as indicated. Finally, we also consider the area of a circle where we have the center point and the radius are given. Now the area of a circle, of course, will be pi times the square of the radius. And in the same instance, we might as well look at the circumference of a circle, and that, you should also recall, is given by the formula 2 times pi times the radius. Now this gives us the area formula for the familiar basic shapes. Next, we will look at two examples where we calculate the areas of particular shapes, and we make use of the theorem of Pythagoras. Let us calculate the areas of the given shapes. First of all, we have this parallelogram, and we have to find the area of it. Now we see in this case that the one side length B is equal to 8 plus 3 centimeters, that is 11 centimeters. We're given that part of the particular side length is 8 centimeters as indicated, and then the rest of the side length is 3 centimeters. And we know for a parallelogram that parallel pairs of side lengths have equal length. So in this case, B will be 8 plus 3 or 11 centimeters. So if we have the side length of a parallelogram and the distance between the two parallel sides, indicated by h in this case, then we are able to find the area of this parallelogram, of course. So we construct a line from the one vertex as indicated, perpendicular onto the parallel side, and create a right triangle as indicated on the screen. So clearly the distance h in this case between the two parallel sides will be the square root of 5 squared minus 3 squared from the theorem of Pythagoras. And in this case, if we calculate that, square root of 16 is equal to 4 centimeters. So we know that the distance between the parallel sides, in this case, indicated by h, is 4 centimeters, and the side length itself is 11 centimeters. So we can calculate the area as b times h in this case, which gives us 44 square centimeters, or centimeters squared for that matter. So that's the first example, where we apply the theorem of Pythagoras to in fact find the distance between the two parallel sides of a given parallelogram, of which we have to calculate the area. Another example, let's have a look at this particular triangle where the two sides are equal as given. So in fact we have here an isosceles triangle. The side length is given as 7 centimeters, and the other side length as indicated. The base, as we will look at this particular triangle to find the area, is 5 centimeters. We make a little construction and use the 5 centimeter side length as the basis, and drop a perpendicular line from the vertex opposite to that side length onto the base, or the side length itself, dividing the side length into two equal parts, in this case of lengths 2.5 centimeters each. And of course we create two right triangles in such a case, and the area in this case will be calculated as half times this base times the vertical height h as indicated. Now how do we find this vertical height h? By the theorem of Pythagoras, that will be the hypotenuse side squared minus the base side, in this case, which we know, 2.5 centimeters for this right triangle, all squared, and the square root of that. And this gives us then the height of such a triangle overall. The base being length 5 centimeter, we're able now to calculate the area as half times the base b times the height h. And substituting the values that we have available, we have this as the area or the area for this particular triangle as 15 times the square root of 19 divided by 4. That is centimeters square in this case. Or that's more or less in decimal format, 16.34587. That is to 5 decimal place accuracy, centimeters square. That's another example then of how we make a little construction and to create the opportunity to apply the theorem of Pythagoras in order for us to find the vertical height of a triangle. That will then in turn put us in a position to find the area of such a triangle. We will now consider the effect on area if a dimension is multiplied by a constant. Note that all areas of shapes can be written as a constant times the product of two length measures. That is, the area A of a shape is always directly proportional to the product of two length measures. This means that the area A can be written as a constant C times the product of the two length measures L1 and L2, for example. Let's just see how this works out in practice with the well-known shapes that we have considered thus far. For example, the area of a square is the constant 1 times, obviously, the square of a side length. This is the product of two length measures. Rectangle, product of the length and the width, for example. For a triangle, we're looking at the constant 1/2 times, in this case, the base length and the height as the other length measure. For a trapezium, we're looking at 1 times the distance h between the two parallel lines or parallel sides times the average of the side lengths of the parallel sides. For a parallelogram, we have the constant 1, in this case, times, in this case, the base length, and of course the distance h between the two parallel sides, of which the base length is actually the reference. For a circle, we have the constant pi times the product of the radius with itself, radius squared. So can you see that in all cases of these shapes we have that the area in fact is determined by the product of two length measures. If one of the dimensions or length measures is multiplied by a factor k, say, then the resultant area A2 will then change by the same factor. In other words, if you have an area A1 and you multiply one of the length measures, either L1 or L2, with a constant k, the resultant area will also change by the same factor. So the second area or the resultant area will be k times the original area. On the other hand, if both the dimensions are multiplied by a factor k, constant k, then the area A2 will change as indicated, since we're multiplying both the length measures with a constant k, to become k squared times the original area. Note that is important. If both the length dimensions are multiplied with a constant k, then the resultant area will change by a factor k squared. For example, if one dimension is multiplied by a factor 3, then the area A2 will be 3 times the original area A1. In the second case, if both dimensions are, for example, multiplied by the factor 4, then the area A2 will be 4 squared times the area A1. In other words, 16 times the area A1 in such a case. Let us now consider a second tutorial which deals with the areas of shapes. Here we have two problems for you to consider, and you have to calculate the areas of the given shapes. First of all, the area of a triangle, and secondly, that of a trapezium. So, at this point in time, I suggest that you pause the video, do tutorial 2, and then come back and view the solutions. Let us have a look at the solution for problem 1 of tutorial 2. In this case, we have to calculate the area of the given shape. This is a regular polygon of order 3 or an equilateral triangle with side length 10 centimeters as indicated. To start out with, like we did in the lesson, we make a construction. We drop a perpendicular line from the vertex as indicated onto the base side length 10 centimeters, and in such a case we establish the height h for this particular given triangle. Note that we create a right triangle in such a case with sides 10 centimeters for the hypotenuse and 5 centimeters for the one side adjacent to the right angle. So in that case we can now find the length or the vertical height h of this particular triangle by making use of the theorem of Pythagoras. H will be the square root of 10 squared minus 5 squared if you apply that theorem, or the relationship between the three sides in the right triangle as indicated. So the area then will be a half times the base b times the vertical height, substituting what we have established for the height h in the position and the base. Of course the length is 10 centimeters. We have then after we have calculated 43.30127 up to 5 decimal places as the area for this particular triangle in square centimeters. You can also express this in surd form as 25 times the square root of 3 square centimeters in such a case. Let us have a look at the solution for problem 2 of tutorial 2. Here we have to calculate the area of the given shape, that is, of the trapezium. So, to establish the parallel side lengths, we see that, let's say, side A has length 18 centimeters, and the second parallel side has length B is equal to 32 centimeters. That is the sum of the parts 9 centimeter length and 23 centimeter length parts of the one parallel side as indicated. So with that in hand, we have our h, the distance between the two parallel sides, as being the one unknown side length of the right triangle as indicated on the screen, where the hypotenuse side is 15 centimeters as given, as well as the base side for this right triangle is 9 centimeters. So we can apply the theorem of Pythagoras once more to establish the distance between the two parallel sides of this trapezium. So h in this case is the square root of 15 squared minus 9 squared. If you calculate that, we get 12 centimeters. Now this is sufficient for us to calculate the area of this shape as being the height, the distance between the two parallel sides h in this case, multiplied by the average length of the two parallel sides. That's a plus b over 2. Substituting the values and calculating, we find that the area of this shape is 300 centimeters squared, or square centimeters for that matter. In lesson 3 of this video, we will focus our attention on surface area and volumes of right prisms and cylinders. Let us have a look at the outcomes for lesson 3. In this lesson, we will focus on two-dimensional net representations linked to three-dimensional solids. Secondly, we will consider surface area of right prisms and cylinders. And finally, we will consider volumes of right prisms and cylinders. In this part of the video, we will consider right prisms and cylinders. Let us start by defining a right prism, or alternatively as a special case, a cylinder. A right prism is a geometric solid that has a polygon, alternatively in the case of a cylinder, a circle as a base and the vertical sides perpendicular to the base. the base and top surface are the same shape and size in all cases. It is called a right prism because the angles between the base and the sides are right angles. Next, we will show a number of basic examples of right prisms and a cylinder. We will start off by the triangular prism. Now, it's clear that the base as well as the top of this particular prism will be a triangle, and the sides, as indicated, will be rectangles. So this is the first example of a right prism called a triangular prism. Next, we have the well-known cube, where the bottom and the top, in this case, will be a square, and so will the sides be, the four sides as indicated, and the sides again perpendicular with respect to the base and the top. Similarly, in the case of a rectangular prism, where the base and the top both are identical rectangles in this case, and so will the sides be, the four sides as indicated, which will be perpendicular with respect to the base and the top. Next, we consider the cylinder, where we have the base and top two identical circles, and we have the side, in this case, perpendicular with respect to the base and top as circles, being the curved side as indicated. This then, the cylinder, as a special case of a right prism. We also have the pentagonal prism, where the base and the top are pentagons, regular pentagons in this case. So the sides, in this case, 5 sides around perpendicular with respect to the base and the top again, will again be rectangles. And finally, another example of a right prism will be a hexagonal prism. Hexagonal because the hexagon, the bottom and the top in this case, will be perpendicular with respect to the sides, again represented by rectangles, as you can see. So 6 sides in this case, and a base and a top being a hexagon in this case to form the hexagonal prism. We will now consider the representation of surface areas of right prisms and the cylinder from nets. First of all, the surface area of any three-dimensional object, and that includes right prisms and the cylinder, is the total area of the exposed or the outer surfaces of such an object. Now, nets of right prisms and cylinders are formed when we unfold the outer surfaces onto a two-dimensional plane into what we call a net, and then we can clearly see each of the faces that make up the right prism or the cylinder very clearly. In order to calculate the surface area of the right prism or the cylinder, we can simply then calculate the area of each of the faces and add them all together. That is, the faces that are represented by the unfolding of the sides into a two-dimensional net. Let us have a look at a number of examples where we use two-dimensional nets to represent the outer surface of right prisms and the cylinder. We will start by considering the cube. If we unfold the sides of this cube onto the plane, we have a representation like we see below. So this then represents the net representation of a cube in this case. And in the second case, if we look at a triangular prism and we unfold the sides similarly onto a plane, we form the net as indicated, with the triangular base and top being represented, as well as the 3 sides being represented by the rectangular strips as indicated in this net unfolding of the three-dimensional object. If you consider, for example, the pentagonal prism, and we unfold the sides, the 5 sides similarly, together with the pentagon which makes up the top and the bottom, then we have something which looks like this. So this is then a representation of a net for a pentagonal prism that we considered in the previous slide. Finally, if we consider a cylinder and we unfold the side, it's unrolling the side onto a plane. Then we have a rectangular shape together with the two circles, the bottom and the top being the circular faces for this particular cylinder, and such a representation is referred to as a two-dimensional net for a cylinder. So in all cases, the total surface area, outer surface area of such a right prism as well as the cylinder in such a case will be 2 times the area of the base plus, in this case, the perimeter of the base times the height, which will give us the area in total of the sides which are perpendicular with respect to the base as well as the top. So note, the surface area in total, outer surface area that is, of a right prism or a cylinder will be given by this particular formula, and that is what we will consider in special cases in the next slides. Note that the height referred to here will be the distance between the base and the top of either the prism or the cylinder, and in the case of a cylinder the perimeter is known as the circumference in such a case. Let us consider an example where we find the surface area of a rectangular prism. Here we have the representation of such a rectangular prism with the 3 length measures L, B and H representing length, breadth and height respectively. From the previous slide we know that the surface area or the outer surface area will be twice the area of the base plus the perimeter of the base times the height. And in this case, of course, this translates to 2 times L times B. Remember, L times B represents the area of the base. The area of the rectangular top in this case will be identical. So we look at 2 times L times B plus, then the perimeter of the base will be given by the formula 2 times L plus B. Just see that you agree. That's just a rectangle. The perimeter for the rectangle will be twice the length plus twice the breadth, and this we can write in algebraic form as 2 times in brackets L plus B. That must be multiplied with the height H. So we have the formula for the outer surface area of the rectangular prism. If we can look at a specific example where L is equal to 10 centimeters, B is equal to 5 centimeters, and H is equal to 3 centimeters, then if we substitute in the right positions in this case, we see that a rectangular prism with these dimensions as indicated will have an outer surface area of 190 centimeters square or square centimeters. In the next example we show the surface area calculation for a cube. Here we have the representation of the cube, and let's say the side lengths will be S in this case for the given cube. Now in this case the surface area, remember we have in this case the top, the bottom will be squares as well as the 4 sides in this particular case. So the surface area in general will be 2 times the area of the base plus the perimeter of the base times the height. In this case, clearly, the surface area will be 2 times S squared. That is the area of the base, S squared, the square. And you have to add then the areas for the 4 sides, which will also be exactly the same squares, namely the squares with area S squared, S times S. Adding all of this together, we see that the surface area of a cube with a length of a side S will be given by 6 times S squared. In a particular case, if we have an example of a cube where the side length is 5 centimeters, then clearly the outer surface area for such a cube will be 6 times 5 squared or 150 square centimeters or centimeters squared. We will now demonstrate how our strategy can be utilized to calculate the surface area of a cylinder. Let's consider a cylinder where we have the base, a circular base with radius r, and h the distance between the circular base and the top as indicated. Now remember our strategy in general for finding the surface area, outer surface area, will be to take 2 times the area of the base and add to that the circumference of the base, since it's circular, times the height in such a case. So here we have then the formula for the surface area of a cylinder, starting with the area of the circular base, which will be pi r squared times 2. Add to that, in this case, the perimeter or the circumference of the circular base, which is 2 pi r, times h, that is the distance between the base and the top of such a cylinder. Taking 2 pi r as a common factor, we have that it must be multiplied in brackets by r plus h in such a case. This gives us the formula for the outer surface area of a cylinder. If we apply it in the case where we have a cylinder with radius 7 centimeters and height 12 centimeters, then we see in such a case, where we substitute the values in the correct positions, we have that the outer surface area of such a cylinder will be 266 times pi square centimeters, or centimeters squared, which if you calculate, check this, use your calculator, it will be approximately equal to 835.6636 square centimeters. That is accurate up to 4 decimal positions. The next question that will be considered is how to find the volume of right prisms and the cylinder. In general, the volume of any right prism will be given by the area of the base times the height. The height, of course, is the distance between the base and the top for these objects. Let's consider the first example where we look at the volume of a rectangular prism. The dimensions of the prism in this case is the length L, the breadth B, which forms together the basis or the rectangular base for this particular prism, and of course the height h represents the distance between the bottom and the top rectangular sides of this particular right prism. In this case, the area of the base times the height translates to the product of L and B and H as indicated. L times B, of course, is the area of the base, and H the height, in this case, between the base and the top, the distance between the base and the top. So a very simple formula then. If you consider, however, the triangular prism, in this case the triangular prism lies on its side, and the triangular base as well as the top, the distance between the base and the top is in this case represented by capital H, so we refer to this then as the height. And looking at the base as such, we need to find the area of the base, and in this case if we just look at this base as being an isosceles triangle, the two side lengths equal, drop a perpendicular from the vertex onto the opposite side of this base, and we have the base length small b, we know that the area of this particular base is given by a half times the base times the height, in this case small h because it refers to the height of the triangular base, times capital H, which represents the distance between the base and the top in this situation. So the volume of a triangular prism is then given by half times the base times the height of the triangular base in this case, everything multiplied by the distance between the base and the top, represented by capital H in this case. Also, if we look at the cylinder, what will be the volume of the cylinder? We need to find the area of the circular base in this case, times the height as indicated, being the distance between the base and the top of the cylinder. And if we substitute, the area of the circular base will be pi times r squared, times the height, in this case h, gives us then the formula for the volume of a cylinder with radius r and with height h, in this case being the distance between the base and the top of the cylinder. I think it's time now for you to consider a tutorial on the surface area and volumes of right prisms. So in tutorial 3 we have the following problem. Calculate the surface area and volume of the triangular right prism demonstrated on the screen. Here we have the triangular right prism, and it is given that the triangular base has the side length B is equal to 8 centimeters, the vertical height h as indicated 3 centimeters, and the distance between the base and the top of this triangular right prism is capital H equal to 12 centimeters. At this point in time, I suggest that you pause the video, do tutorial 3 and then come back and view the solutions. Let us have a look at the suggested solution for the problem in tutorial 3. In this case, we had to find the surface area of a given triangular prism, which is always twice the area of the base triangle plus the perimeter of this base triangle times the height of the prism. So we have a right triangle with sides linked to the right angle, 4 centimeters, half the side length that is given, B is equal to 8 centimeters that is, and of course the other side will be the side H, in this case equal to 3 centimeters. If we say that the unknown side is denoted by A, then we can calculate A using the theorem of Pythagoras in this case by the square root of 3 squared plus 4 squared, which gives us 5 centimeters. So we know that the second side length of the isosceles triangle is 5 centimeters. Then we're ready to find the surface area of this triangular prism as twice the area of the triangular bases, half times B times H, plus, in this case, the perimeter of the triangular base, 2A plus B for the isosceles triangle, times the distance, capital H, between the base and the top of this particular triangular prism. If we substitute the values in the correct positions and calculate, we find that the outer surface area for this triangular prism then is equal to 240 centimeters squared, or square centimeters. In order to find the volume of the triangular prism, we make use of our basic formula, that is the area of the base triangle times the height or the distance between the base and the top for this prism. And if we substitute all the values in the correct positions, then we can actually calculate and find that the volume of this particular triangular prism will be given as 144 centimeters cubed, or cubic centimeters. In lesson 4 of this video, we will consider surface area and volumes of right pyramids, cones and spheres. Let us have a look at the outcomes for lesson 4. In this lesson we will focus on surface area of right pyramids, cones and spheres, and also volumes of right pyramids, cones and spheres. We will start this lesson by considering a general approach for finding the surface area and volume of right pyramids and cones. Let us consider the first example of such a structure, a right pyramid that is. Here we have a square base, and the slanted sides, 4 of them as you can see, tapers smoothly from the base to the top, which is referred to as the apex or vertex for this particular right pyramid. The right means that if you drop a perpendicular from the apex down to the base, it will actually meet the center point, in this case of the square base. Similarly, we have a right pyramid where the base is a equilateral triangle as indicated, and in particular a special case where the base is a circle and we have the side as a slanted side tapering off to the apex. The right cone in this case will then be the cone where you drop the perpendicular from the apex down to the center of the circular base. Note that in the CAPS document the focus is only on right pyramids where bases are either an equilateral triangle or a square, and alternatively a circular base, which gives us the right cone in such a case. Now, the surface area of a right pyramid or a cone for that matter, is always equal to the area of the base plus a half times the perimeter of the base, and in the case of the cone it will be the circumference of the circular base, times the slanted height. Note, this is the distance between the base and the apex, the slanted height. That is for the surface area of right pyramids and the cone in this particular case. The volume of a right pyramid, on the other hand, or a cone for that matter, will be 1/3 of the volume of the right prism containing it. Refer to the earlier lessons to see what the volume of the right prism will be that contain this particular right pyramid or cone structures. So we have the volume then as 1/3 of the volume of the corresponding right prism containing it. We will now consider formulae to calculate the surface area of the two right pyramids as well as the cone that we have considered in the previous slide. First of all, let us consider the right pyramid where we have a square base as indicated. Now in this case, the base has length b, for example, for the square, and hs is the slanted height. Now that of course is the distance between the midpoint on any one of the sides of the base as indicated along the slanted surface up to the apex, that particular distance. If you drop a perpendicular from the apex in this case down to the midpoint of one of the sides of the base, that distance is our slanted height, and that will be denoted by h sub s in this case. And of course we have the height of the pyramid, the distance between the apex and the bases as indicated if one drops a perpendicular down to the center point of the square base. With that in hand, we can now give a formula for the surface area of a square pyramid, in this case the right square pyramid, that is. It will be the area, as we've seen on the previous slide, of the bases, which is b squared, plus a half times the perimeter of the square base, which is 4 times b, times the slanted height as we have explained it. Next we consider the right pyramid where we have an equilateral triangle as a basis, as can be seen on the screen. In this case we have to consider the following parameters before we give this formula for the surface area of such a right pyramid. We have that the base length is b, that is the sides of the triangle, each one of them is b, for example, and h sub b is the height of the base for this pyramid, the triangular base. That is the distance between the midpoint of one of the sides and the vertex opposite to that side. So you can choose any one of the sides as your basis. Look at the midpoint for the base and a line from the opposite vertex to that particular point will be perpendicular on the base, but that distance will then be the height of the base triangle in such a case. We have another height to consider in this case. Again, the slanted height, h sub s, will be the distance from the midpoint of any one of the slides to the apex along the slanted surface as indicated. So if you drop from the apex a perpendicular line onto the midpoint of one of the three sides of the equilateral triangular base, then we have the slanted height h sub s. Capital H in this case will again be the height of the pyramid as a whole. That will be the perpendicular distance from the apex down to the triangular base. With those parameters in hand, we know that the surface area of a triangular pyramid, that is a right triangular pyramid in this case, will be, as discussed, the area of the base, the triangular base, will be a half times the base times the height of the triangle base in such a case, plus a half times, now the perimeter in this case will be 3 times b, 3 side lengths of the equilateral triangle, times the slanted height h sub s. So there we have the formula for the surface area of a right triangular pyramid. And finally, if we consider a cone where the circular base has radius r, and we have that the slanted height is in this case again denoted by small h, where the height of the cone is capital H in the usual way, we have the following. So R the radius, H the slanted height, and capital H the height of the cone. The surface area of a cone with those dimensions will be the area of the base, which is pi r squared for the circular area in this case, plus half times the perimeter of the base, which is the circumference of the circle, 2 pi r, times the slanted height. And this can be simplified as indicated by pi r in brackets times r plus h. So there we have the formula for the surface area of the two right pyramids as well as the right cone. Finally, we will consider the formula to calculate the volumes of right pyramids and cones. As in the previous slide, we will start with a square pyramid with the parameters b, the base length, h sub s, the slanted height, and capital H, the height of the pyramid as before. In such a case, the volume of a square pyramid is given, remember, in general, it's the third of the area of the base times the height. So in this case, it will be a third times b squared times capital H. In the case of the triangular pyramid with the parameters as seen before, b the base length for the equilateral triangular base, h sub b is the height of the base triangle, h sub s is the slanted height, and capital H is the height of this pyramid, we have the formula for the volume as follows. The volume of a triangular pyramid is given by a third again, times the area of the triangular base, which is a half, times the base length, times the height of the base triangle, everything times the height of the pyramid, capital H, in such a case. And finally, for a cone with the dimensions as seen before, r being the radius of the circular base, small h the slanted height, and capital H the height of the cone, we have that the volume of a cone with these dimensions is given again by a third times the area of the circular base, pi r squared, times capital H, which is the height of this particular cone. Next, we will consider the surface area and volume of a sphere, and also give a formula for both the surface area and the volume. Here we have a sphere, and what is important in this case is the radius of a sphere in order to find the surface area and the volume in such a case. So the distance between the center of a sphere and the surface area is constant, and it's indicated by the parameter small r representing the radius of a sphere. Now in such a case, the surface area of the sphere will be given by the formula 4 times pi times r squared. That is the outer surface area exposed to the outside of this particular sphere. Similarly, the volume of the sphere with the radius r is given by the formula 4 over 3 times pi times r to the power 3. Remember, volume is a three-dimensional entity or unit, whereas surface area in general, is two-dimensional, and the exponent indicates that in both of these formula. Let us consider an example of where we calculate the surface area and the volume of a particular cone. Question is, find the surface area and volume of a cone with radius 3 centimeters and slant height or slanted height 5 centimeters. Now here we have the cone, the construction of the cone. As we can see, the slanted height, let's denote that by S, is 5 centimeters, it's given. And also the radius in this case is given as r equal to 3 centimeters. First of all, let's consider the surface area. Recall that the surface area will be the area of the circular base plus a half times the circumference of the circular base times the slanted height. In this case, if we substitute, we see that the base, of course, is represented by pi r squared, and also the half and the 2 will cancel, and we have pi rs for the second term. Taking pi r as a common factor, pi times r, we have in brackets r plus s. So we substitute the values for r and for s as indicated, and we have that the surface area of this cone is given approximately as 75 0.398 to 3 decimal place accuracy square centimeters or centimeters square. In order to calculate the volume of a cone, we need the height of this particular cone, so we need another construction. The distance between the apex of the cone and the center of the circular base, capital H, is what we need in this particular case. And that we can find by applying the theorem of Pythagoras to find the distance between the apex and the center point of the circular base. Since we have here a right triangle, if you consider that particular line from the apex to the center of the circular base as the one side of the triangle, the right triangle that is, and also the radius line will be the other side, and we have the slanted side, in this case a distance is as 5 centimeters. So the only outstanding distance in this case will be the one side linked to the right angle as indicated, and we can calculate that. So the distance h, or the height of the cone, will then be the square root of s squared minus r squared in general. We substitute the values for s and r that is available. In this case we have 4 centimeters once you've calculated correctly. So we're ready now to find the volume of the cone, V, as a third times the area of the base times the height of the cone. Substituting the values, in this case we have a third times pi times 3 squared, the radius squared, times 4, and in this case it will be cubic centimeters since it represents volume. So in the end we can leave the answer as indicated as 12 times pi cubic centimeters, or centimeters cubed, for the volume of the cone. I think you're ready now for tutorial 4, where we will have a problem that deals with the surface area and volume of a right pyramid. In this case we have that ABCDE is a right pyramid of which the base ABCD is a square, and this is represented on the screen. We have that FE, the line segment FE, is perpendicular to the line segment AB. And have a look at that. FE is perpendicular to AB. It just says that FE represents the lateral or the slanted height of this given pyramid. And EF is perpendicular on the side of the square base AB, as indicated. Also, EO is perpendicular to the base. That's EO, that's the line that is dropped from the apex or vertex for this pyramid to the center point of the square base. EO is perpendicular to the base, and that represents of course the height of the pyramid as we saw it before. Now with that in hand, first of all, if we say that FE is represented by small l, the parameter small l, and AB, that is the side length for the square base, is represented by the parameter small b, show that the total surface area for any such a pyramid is given by the formula small b in brackets times 2l plus b. That is the first challenge. Secondly, calculate the total surface area of such a pyramid if we're given that BC is 12 centimeters. Remember, BC in this case is just one of the sides of the square base, and FE is 8 centimeters. FE, of course, represents the lateral or slanted height for the given pyramid. Thirdly, in the final instance, you have to calculate the volume for this given pyramid. At this point in time, I suggest that you pause the video, do tutorial 4, and then come back and view the solutions. Now let's have a look at the suggested solution for the problem in tutorial 4, that is part 1 of the problem. In this case, we had to find or to show that the total surface area of the given pyramid is given by the formula b times in brackets 2l plus b, where FE, the slanted height, is L, and AB, that is the side length of the square base, is small b. So let's see how we go along in doing that. Well, the total surface area of a pyramid of this type, in general, recall, will be the area of the base plus 4 times the area of these slanted triangles. Each of the sides represent a slanted triangle. So if you can add the 4 areas of the slanted triangles together as well as the area of the base, then clearly we have the total outer surface area of this right pyramid. You can also choose, alternatively, to use the strategy that we have mentioned during the lesson. That is, that the total surface area in such a case can be the area of the base plus a half times the perimeter of the base times the slanted height. So let's just calculate the surface area using either one of these strategies, and in both cases it must agree with the formula b times 2l plus b as indicated. So in the first instance, the area can be calculated as the area of the base, that's b squared. Side length for the base is b, remember, and the base is a square, plus 4 times, now the area of the slanted triangle in each case for the 4 sides will be a half times the base, in this case it is b again, times the slanted height L, which is given to us. So if we simplify this, we have b squared plus 2bl, which if we take b as a common factor gives us exactly the expression b times in brackets b plus 2l. So that would be enough to prove this particular formula for this given pyramid. Alternatively, you could also consider the area, that is the total surface area for the pyramid, as the area of the base, b squared again, plus a half times, and in this case we need the perimeter of the base, which is of course 4 times b, times the slanted height, in this case represented by the perimeter L. And again, if you simplify, you get exactly the same expression as expected, b times in brackets b plus 2l. So that is part 1 of the problem in tutorial 4. In part 2 of the problem in tutorial 4, we have to calculate the total surface area of the given pyramid if we have that FE is equal to 8 centimeters and BC, that is the side length of the square base, is 12 centimeters. Well, we've established a formula for the surface area in part 1 of this problem, so it's just a matter of substituting the values. That is, in our case, B, which represents the side length of the base, 12 centimeters, and L, the slanted height, is given as 8 centimeters. Substituting and calculating, we see that the surface area of such a pyramid will then amount to 336 square centimeters. In part 3 of problem 1, we have to calculate the volume of this pyramid if we have that the side length for the base, square base, is 12 centimeters and the slanted height is given as 8 centimeters. Now the challenge in this case is to find the height of this particular pyramid, denoted here by EO, and we can see EO and EF and FO forms a right triangle. So we can calculate the distance EO as the square root of EF squared, that is the hypotenuse side of this right triangle, minus the square of the distance FO in such a case. So the challenge then becomes finding the distance FO, because we were given the distance EF. In this case, FO of course is just half times the side length BC, because we have a square side, and from the properties of a square we know that FO will be just half the distance of BC, for example. And that is because F is the midpoint of AB, and we know that the diagonals for a square also intersect at the center point for that particular square. So FO then, half of BC, which gives us 6 centimeters, since BC is 12 centimeters. We're ready now to calculate the height of this pyramid, EO, as the square root of 8 squared minus 6 squared as indicated, and this insert form gives us the expression 2 times the square root of 7 centimeters for the height, EO. With that in hand, we can now calculate the volume for this particular prism as being a third times the area of the base times the height of this particular prism. So it's a third. The area of the base would of course be 12 squared for the square, and the height we've just calculated as 2 times the square root of 7. Putting that together and expressing it in surd form gives us 96 times the square root of 7 cubic centimeters as the volume for this particular pyramid. In lesson 5 of this video, we will consider surface area and volume of combined solids. Let us consider the outcomes for lesson 5. In this lesson, we will focus on surface areas of combined solids, secondly, volumes of combined solids, and finally, we will investigate the effect on volume if 1, 2, or all 3 the dimensions of a solid is multiplied by a constant factor. In some cases, we have to find the surface area or the volume of a combination of these right pyramids and other regular objects. In this example, we look at the case where we combine the cube and the pyramid. So here we have the object or the combined solid where we combine the cube and a square pyramid as we have seen before on top of the cube. The total height is given as 11 centimeters. That is from the bottom of this particular cube, the base, to the apex of the square pyramid that is placed on top of the cube. The side length of the cube is 5 centimeters. Let's see how we can find, first of all, the surface area of this particular combined solid. In this case, let's say the side lengths of the cube are S equal to 5 centimeters. We know that the height of the pyramid in this case will be 6 centimeters. That's the difference between the height of the cube, 5 centimeters, and the total height, 11 centimeters in this case. So that's fairly easy to find. However, the slanted height of the pyramid, denoted by small h sub s, is slightly more difficult to find. Here we have to make use again of the theorem of Pythagoras. So we're talking about this particular distance from the apex of the square pyramid, in this case, to the midpoint of the side length, in this case, which is the combined side length for the pyramid and the cube. At the bottom of the pyramid as such, the basis is also a square. That distance, of course, if we take that point at the base, midpoint of the side, in this case, towards the center of the base for the right pyramid, and from there right to the top, we have a right triangle, as we saw earlier in this lesson, and we can make use of the theorem of Pythagoras because we have the height, the vertical height, as 6 centimeters, and the distance from the midpoint of the square base for this particular right pyramid and the midpoint of one of the sides at the bottom will of course be 5/2. It's just half the side length. So substituting the values, making use of the theorem of Pythagoras, we see that the slanted height of the pyramid is given as 13 divided by 2 centimeters, or 6.5 centimeters. With that in hand, we're now ready to calculate the surface area of this combined solid. Clearly we have to add the surface area of each of the square faces to each other, 4 of them, and the bottom. So we have 5 times s squared. Note that the top of this cube does not belong to the outer surface area of this combined solid at all. So we have 5 times s squared, and adding to that half times the perimeter of the bottom or the base for this square pyramid, namely 4 times s, times the slanted height, and that will give us the area. Substituting the values in the correct positions, we have in the end that the outer surface area for this particular combined solid will be 190 square centimeters, or centimeters squared. For the volume, of course, we have the formula. For the cube, we have s cubed. That is the volume of the cube part of this combined solid, plus the right pyramid on top of it will have a volume of 1/3 times the area of the base, s squared, times, of course, the vertical height, h, which we have as well. So substituting the values in this case in the right positions and calculate, we find that the volume of this combined solid will be given by 175 cubic centimeters or centimeters cubed. Next, we look at the effect on volume if one dimension is multiplied by a constant. In general, volume of any solid will be directly proportional to the product of three independent length measurements. That is to say, volume can be written as a constant times the product of the three independent length measurements, denoted here by L1, L2 and L3 respectively. We can actually demonstrate this. Let's say we have, in this case, a rectangular prism, and the measurements will be L, the length, the breadth, B and H for the height, for example. Then the volume of the solid, of course, V sub 1, say, will be the product of L, B and H, as we saw before. If we multiply one of the dimensions, say by a constant 5, then the volume of the resultant solid will obviously be different to what it was before. So if, for example, we have changed the height and make it 5 times what it was before, then this is the net result, and the volume accordingly will become 5 times more than what it was before. So V2 will be the length, the breadth stayed the same, and now we have a volume of 5 times H, which means that the volume changed by a factor 5 in this particular case. So in general, we can say that if one dimension of a solid is multiplied by a factor k, say, then the volume of the solid increase by the factor k in general. In this case, of course, we assume that the factor k is positive. In a similar way, we can investigate the effect on volume if two dimensions are multiplied by a constant. We have exactly the same situation. A volume V1 determined by the three length measurements L, B and H as before. So we're looking at a rectangular prism as an example, and in this case, if we multiply two dimensions by the constant 5, let's see what happens. So in this case, let's change the length to 5 times what it was, to 5L, and let's change the height H to 5H, 5 times what it was. So if we consider the volume of the new solid, then we have the volume in such a case will be 5 times the original length times the breadth, which stays the same, times 5 times the height. In this case then we have 25 times the volume that we started out with, or 5 squared times the original volume. So we can say in general then, for a two-dimensional change or multiplication by a constant, if two dimensions of a solid is multiplied by a factor, say k, which is greater than 0, then the volume that results of a solid will then increase by the factor k squared. Finally, the effect on volume if all three dimensions are multiplied by a constant can be demonstrated again by this example that we saw before. So if we multiply all three dimensions, say by the constant 5, then this is what the result will be. So the length became 5 times more, so did the breadth, and so also the height. So in this case, if we look at the volume of the new solid, then clearly it becomes 125 times the volume of the original solid. This can be expressed as 5 to the power 3 times the original volume that we started out with. So we can state here also, if three dimensions of a solid in general is multiplied by a factor k greater than 0, then the resultant volume of the solid will increase by the factor k to the power 3, or k cubed in such a case. I think you're ready now to tackle a tutorial on the area and volume of combined solids. So here we combine a cube and a hemisphere as part of tutorial 5. Now a hemisphere is just half a sphere, which is placed in this case on top of a cube of side length 3 centimeters as indicated. So the question here is to find the total surface area, outer surface area, and the volume of this composite object or combined solid. At this point in time, I suggest that you pause the video, do tutorial 5, and then come back and view the solutions. Let us have a look at the suggested solutions for problem 1 of tutorial 5. In this case, we have to find the outer surface area of the given combined solid. Now this is a combination of a cube and a hemisphere or half a sphere placed on top of the cube as indicated. In order to find the area, we first of all consider the areas of the 5 square faces for this particular cube, that is the 4 along the side and the bottom. Together we must then add the exposed area of the top part of this particular solid, which consists of the area of the hemisphere on top, and that is what we calculate next, half times the area of the sphere, 4 pi r squared. And then of course we need to find the areas, the exposed parts of the top face not covered by the circular base for this particular hemisphere that was placed on top of it. And to get that, we need to subtract the area of the circular base of the hemisphere from the square face which forms the top of the cube. And in order to do that, we get the area of the top, the square top of the cube, subtract from that the area of the base, the circular base for the hemisphere that was placed on top of the cube. This gives us then the formula for the area, surface area, for this particular combined solid. Substituting for the parameters S and R in the correct positions, in this case, the side length being 3 centimeters, we calculate and find that the area in this case is given as 61.06858, that is to 5 decimal place accuracy, square centimeters or centimeters square. It can also be expressed in this format. The numerator position 216 plus 9 pi, everything divided by 4 square centimeters. To find the volume, secondly, of this particular combined solid, we have the volume of the cube, it's part of the total volume, the s to the power 3 if the side length is s, and then of course we need to find the volume for the hemisphere, which is half times the volume of a sphere with radius r in this particular case. Substituting the values once more, s is equal to 3, and in this case we know that the radius r is 3 over 2. We have the volume given approximately equal to 34.06858 cubic centimeters, that is again to 5 decimal place accuracy in this particular case. In the final tutorial, tutorial 6, we look at a problem where we have to find the volume and the surface area of a combined object where we have the cylinder combined with cones. So here we have the problem. A solid metal object is formed by placing 2 identical right cones at each end of a cylinder as indicated on the screen. The total length of the object is 36 centimeters and the cylinder is 20 centimeters long and has a diameter of 12 centimeters. So all the information now indicated. We have the diameter of the cylinder 12 centimeters and the total length of the object 36 centimeters, where the total length of the cylinder or the height of the cylinder will be 20 centimeters. With that in hand, calculate the volume of the combined solid. At this point in time, I suggest that you pause the video, do tutorial 6 and then come back and view the solution. Let us have a look at the suggested solution for the problem in tutorial 6. Here we have this combined solid again with the dimensions as indicated for the total length of the solid and for the length of the cylinder in such a case. The diameter of the cylinder is given again 12 centimeters, and in this case we need to just make sure that we subtract the length of the cylinder from the length of the total object and divide by 2 to get the height of the right cones. In both cases it will be 8 centimeters. These are two identical cones. The bottom cone is just placed upside down, and the top cone in this case as indicated. So the height of each of these two cones will be 8 centimeters. The radius of the cone, and the cylinder for that matter, will be half the diameter, which is 6 centimeters. We're ready now to find the volume of this composite solid as being the volume of the cylinder, and we have to add to that twice the volume of any one of the cones. So for the volume of the cylinder, clearly we need to find the area of the circular base for the cylinder times the length or the height of the cylinder which we have available, plus twice the volume of the cone, being a third, times the area of the circular base times the height of the cone. Substituting the relevant values, since we have all of them available, and consolidate, check the algebra in this case, we arrive at an answer approximately equal to 2865,13 cubic centimeters. Check with your calculator that you agree with this answer to 2 decimal place accuracy. We have come to the end of the video on surface area and volume. Remember, consult textbooks for additional examples. Attempt as many as possible other similar examples on your own. Compare your methods with those that were discussed in the video. Repeat this procedure until you are confident. Do not forget, practice makes perfect. Good luck and goodbye.